Hi, my name is Kevin Farlee. My partner David Pless and I are presenting a pair of talks on SQL Server 2022 engine features and capabilities. David has a session that was presented that went over features of the storage engine specifically, and here I'll be focusing on the high availability and disaster recovery features. So you hear a lot of talk about HADR, HADR, as if it is a thing. So let's dive a little bit into what is this HADR thing? What is HADR? Some context about high availability and disaster recovery. So it's not one monolithic thing, HADR. It's actually two separate concepts, uh, disaster recovery and high availability. So let's tease those apart just a little bit. Disaster recovery is recovering from an event that takes a large part of the infrastructure offline, a site or regional outage. This isn't about one system went down. This isn't even about a couple systems or a minor network went down. This is the whole site is offline and unavailable. Sort of like that. Have that picture in mind when you start talking about disaster recovery. So for disaster recovery, you need to assume that the primary site, at least, is not accessible for some extended period. And by not accessible, I mean no communication whatsoever. Communications may not be possible. It may be that communication lines have been completely severed and you can't talk to anybody. It may be that the building is a smoking hole in the ground. You don't know. So the point is that you have to rely entirely on resources, people and equipment at some remote location. That's why people have DR sites. So if the whole region is cut off, then you have another location where you can continue to run your business. Usually, getting back online and available is more important than not losing any data. That's not to say that it is ever okay to lose data. It is not. But there are times when you need to make trade-offs between getting back online quickly and get your business running and retrieving the last few seconds of transactions. And most times, once the dust settles, you'll be able to go back and retrieve that data. But in the moment, getting back online and available is far more important. High availability, on the other hand, is maintaining the availability of a surface or a system with an absolute minimum, ideally zero downtime for any reason. It doesn't matter if you planned it or not. So taking a system down to do maintenance is downtime. Taking a system offline for backups or whatever, that's all downtime, and it counts against your metrics. So typically, companies will publish specific metrics for what their availability is going to be, and it typically represented as a percentage of the possible uptime. So you'll hear 99.999% availability, which is referred to as 5 nines, right? So 4 nines, 5 nines, 6 nines, whatever it works out to be. And that's your commitment to what percentage of the entire time frame your systems will be completely available and running. Just for context, 5 nines works out to 5 minutes and 15 seconds of acceptable downtime per year. This is not something to be taken lightly. You take a system down, sometimes just taking a system down and rebooting it is enough to go over that threshold if you have some of those monster machines with huge amounts of memory. So any outage, maintenance, upgrade, failure, planned or unplanned, detracts from your HA goal. So you need to really take that seriously. So high availability is about protecting against anything that prevents an application from accessing the data it needs. Obviously, the entire context is more than just the database, but here we're talking from the perspective of SQL Server and your data platform. So assume that site and facilities are not impacted, unlike the disaster recovery. For high availability, you assume that the site and your facilities are there and available to you. Typically implemented via locally redundant equipment. So clusters, availability groups, etc. So if a machine has a fault, it will automatically fail over to another machine running in parallel, keeping up so that you can keep business going without any significant downtime. Outages are typically measured in seconds, sometimes minutes. And your metrics for high availability are RPO and RTO. So what do those mean? So RPO is recovery point objective, which means if the system went down, how close to that instant in time can you get? So if you have to restore backups, can you get to that exact instance, or can you only go to when the last backup happened, which may have been a minute before or an hour before? So those are different RPOs. RPO of a minute, RPO of an hour, RPO 0 is what you want ideally. RTO is the time it takes to get there. From whatever failure happened to back online and processing, that's your recovery time. So RTO, you want as close to 0 as well. Whatever you do should not result in any data loss. So you're aiming for RTO of 0 at all times. I'm going to go over a brief history of HADR features in SQL Server. We always talk about the newest features, but it's important to understand that we've been at this for a while and we've been progressing year over year, release after release, and it's been quite a journey. So let's go through that journey. So starting in SQL Server 2000 SP4, we had introduced failover clustering and log shipping, backup restore. With SQL Server 2005, we brought in database mirroring. So that was the ability to have two machines, two instances of SQL Server where we were shipping updates from one to the other. And you could do some manual operations to bring up the second as the primary, but it was far from seamless. Still, it was a significant step. Database snapshots, the ability to take a snapshot of a database at a point in time so you can do analysis on a fixed set of data rather than having it moving underneath you, or to have that available to revert to at some later point. Checksum validation and read retry. So within database snapshot, we have two copies of the same data each running on an instance. Checksum validation, whenever we read a database page, there's a checksum on it, and we validate the checksum to make sure that the data is intact and valid. With two copies of the data, you have a unique opportunity where if a checksum validation on your primary copy fails, so you know you have some corruption on that page, we can go inquire of the partner in the mirroring relationship, say, did this page read clean? And if it did, send your copy over and we'll automatically pull in the copy from the database mirroring peer, and then we'll use that to fix the page on your live database. So it's an automatic recovery in that sense. Mirrored backups and media checks, so that means you're able to, when you're doing a backup, send the backup to two targets concurrently. So the same backup stream gets split and sent to two different physical devices, so you have redundancy on the device front. And also media checks, so we're checking the media that you put the backups onto to make sure that you have a solid backup copy. Cost recovery has to do with once you have a database that went down, whether it was for restore, whatever reason, you have to bring the database online. How fast can we bring that database back online and get you up and running? This is a continual process which started in 2005 and continues to this very release. And I'll go over some of those features in a bit. Online restores, so without taking the whole database down, you can restore a portion of your database. Moving on to SQL Server 2008, right ahead on the incoming log stream compression, so we're compressing the log stream and giving it, which results in less I/O to your devices. Automatic recovery of corrupted pages, so this builds on the functionality in database mirroring when we detect a corrupt page. SQL Server 2012 was a major enhancement, so we introduced always-on availability groups within that feature, within that release, and that has become the flagship HA feature within SQL Server. A lot of our newer technologies are built on the core of availability groups. Multi-subnet cluster, so it allows you to have a failover cluster where your two replicas nodes are in different subnets, so you have network redundancy that way. Flexible failover policy, so that gives you the ability to tweak how severe does a problem have to be before it triggers a failover. If it's a minor hiccup, maybe you want to keep it running on the same replica to avoid the disruption of having connections broken and that sort of thing. Moving on to SQL Server 2014, we raised the number of replicas to 8. So you can now have 8 total replicas, secondary replicas on your availability group. Online secondary replicas after quorum loss. So this has to do with after you lose quorum, you obviously can't be processing updates if you don't know which side is in charge due to lost quorum. However, we can service read-only access because there's no risk of data corruption there. So we'll continue servicing read-only connections even after quorum loss, which means your read-only reporting workloads can continue to function. Cluster shared volumes for failover cluster instances. This is a Windows Server feature which we added support in SQL Server 2014. Cluster shared volumes are volumes attached to each physical node within a Windows failover cluster, and the Windows failover cluster binds those two into a single logical volume and keeps the two physical volumes in sync at all times. So that means you have at each node a logical shared volume without having to have the physical connections for a physically shared volume. So it simplifies your setup a little bit. SQL Server 2016 was a big release in terms of HA functionality. We added availability group support for Standard Edition. Previously, availability groups had only been offered in Enterprise Edition, which priced some people out of the market. We wanted to make that technology available to all of our customers to give a standard offering for high availability while still preserving the value in some of the advanced availability group features. So what we did is we created the basic availability group features. Basic availability groups are designed to have the same surface area and functionality as database mirroring, but using all the functionality and technology of availability groups. So it's a much smoother experience than database mirroring was, much less manual, more automatic and seamless. But it gives you the limited surface area that database mirroring did. So you still get value for your investment in Enterprise Edition for full availability groups, but you do get that same technology available for Standard Edition. Load balancing of read intent connections. So if you have multiple secondaries configured to accept read-only connections, read intent, then what this does is we will round robin across the read-only replicas. So we're spreading out that read-only workload. So if you have a really heavy read-intensive workload that does a lot of reporting, analytics, whatever, now you can spread that processing over a number of different replicas as long as the workload is read-only. Three auto failover replicas. Previously you had only two auto failover replicas. Now you can have up to three replicas that are tagged for auto failover, so it gives you little extra redundancy in your failover configuration. Distributed Transaction Coordinator support for AGs. So this means that you can now rely on the DTC semantics for if there is a crash in the middle of a transaction before it is recorded as being committed on both sides. When both sides come back up, DTC is responsible for determining should this transaction be committed on both sides or rolled back on both sides. You don't ever end up with a situation where one side is committed and the other side is not. Database level failover detection. So this adds the ability to, even if the instance is still perfectly healthy, if a database has gone offline because of some corruption or whatever, hardware problems, whatever it might be, your application can't function without that database. So you'd like the AG to fail over to another replica where it does have all the databases accessible, and that's what this accomplishes. Even if the instance is healthy, if any of the databases in the AG fail, will trigger a failover. Distributed availability groups. So this is, think of it as an availability group of availability groups. So you have multiple availability groups that are kept in sync. The original use case was an application which is geographically dispersed and is a read-mostly application. So think about an online chat system where all the writes can be routed to one location, and that would then forward any updates to all of the replicas, but read traffic can be routed to whichever replica is geographically closest. It also means that you don't have to have a common cluster infrastructure between those two. Previously, to have that geographic redundancy meant that you had a Windows failover cluster that spanned that distance. And that can cause issues if there's a network hitch between New York and Oregon, say. Then some things could go offline in Oregon that weren't specifically related to that database. So this just gives a smoother experience that way. It gives you some decoupling. So that's what was added there. Direct seeding of availability replicas. So that's what you're used to by now, which is where when you're adding a database to an availability group or creating an availability group, we will automatically stream the contents of that database to the new replica and create it. So what we're doing under the covers is we're doing a backup of the source database and piping the backup stream over the same transport we use for the AG updates, and then piping it straight into a restore on the other side. So it makes it setting up new replicas much simpler. And we have done some improvements to the log transport to make it more performant. So specifically, we went through the entire transport end to end and reduced or eliminated context switches wherever we possibly could. So that made it much more effective and performant. SQL Server 2017, of course, introduced Linux. So we also have HA support for SQL Server on Linux. Of course, there's no Windows failover cluster. There is Pacemaker and other Service Guard, other third-party clustering solutions on Linux, and we can certainly take advantage of them. full DTC support. So there were some gaps in the DTC functionality when we first introduced it. We fleshed those out in 2017. We also added read scale availability groups. Read scale availability groups, we've talked about the ability to route read-only traffic to specific replicas. Read scale availability groups are able to be set up without any clustering infrastructure underneath. So it's a little different configuration specific to when you have one master and the rest are strictly read-only. New cluster types. So with Linux, we've added new types for clustering. We have mentioned pacemaker, service guard, and there's a couple others. There's also the external cluster type when you're configuring an availability group there. Required synchronized secondaries to commit, which is a mouthful. This is a setting which guarantees you will never lose a partial transaction. And what that means is that when we commit a transaction on the primary, that commit up record gets sent out to the secondaries, and the secondaries have to acknowledge it, synchronize that commit. So before the commit is finalized on the primary, all of the secondaries have to acknowledge that they have received and committed that transaction. One of our developers jokingly refers to this as the anti-availability features, because if one of your secondaries is having problems, that can take the primary offline. But if each transaction means dollars and cents because you're in a commerce sort of application, that may be the right choice. And so that's what this facilitates. SQL Server 2019. We added support for dynamic network names. These are primarily useful in Azure VMs. Previous to this, the only way to set up a cluster within Azure VMs was to use an Azure load balancer, which is a very functional feature, but it can be somewhat daunting to configure at some points. So with DNNs, you don't need to set up that. It relies on different aspects of networking to accomplish it. And Azure Shared Disk Clusters. So we've introduced in Azure Storage the shared disk within Azure, and now we're supporting that within the failover clusters. So now that we've talked about the history of HA features going into SQL Server over the years, we're going to focus now on the new features that we're adding in SQL Server 2022. So we have distributed availability groups with failover with zero data loss. Some availability, perf, and stability improvement. So perf and stability for availability groups primarily. Multi-write replication. Write replication. Managed instance link, which is an interesting feature we'll get into. And finally, contained availability groups, which you may have heard of. Distributed availability groups with failover with no data loss. So distributed availability groups were intended for remote locations. We talked about that a little bit earlier. It resolves quorum issues between sites. So if you have a single quorum across a bunch of sites and there's a network outage, that can cause remote sites to lose quorum and take down any services there, even if they're perfectly healthy. They improve WAN network efficiency and enables mixed Windows versions because you don't have to have a common cluster. Challenges is that there is no central cluster manager, so there's no way to really synchronize failovers. It's been generally very difficult to guarantee zero data loss in failovers because the two sides aren't really talking aren't communicating in terms of which LSNs have been persisted and which haven't. So it can be very difficult. Um, we have changed that with SQL Server 2022 with the zero data loss um, for distributed AG failover. And basically what we've done is added the ability to apply required synchronized secondaries to commit at the distributed AG level. Previously, it's only been available for normal availability groups. And as we talked about earlier, required synchronized secondaries to commit stipulates that the primary replica and the primary AG in this case will not complete a commit until the secondary has acknowledged that it has persisted that commit. So it's a kind of a two-phase commit sequence happening there. And if you can do that at the distributed AG level, we can then guarantee that there's no data loss. So we can ensure that there's no transaction that is partially committed when failover happens. It takes a very complex and error-prone operation and makes it simple and success-prone. Previously, you were having to query each side of the distributed availability group and look at which LSNs had been persisted and find a window when neither side was moving in order to guarantee zero data loss. With this new feature, it becomes very simple because it just set the required synchronized secondaries to commit and it works. And you can set it back to zero if you don't want to have that overhead for normal operations when you're not doing a failover. It doesn't make failover automatic. It doesn't. There are other things that aren't there, but this does guarantee zero data loss. The link feature in SQL Managed Instance. So this is a new, significantly new feature in Managed Instance, which enables you to have a connection between a SQL Server on-premise and a SQL Managed Instance. So you have hybrid connectivity scenarios between the two. It empowers you to immerse into Azure at your own pace. You can modernize in Azure while you keep running in existing SQL Server. When you're ready to migrate to Azure at your own pace with minimum downtime. And then you can use Managed Instance as a disaster recovery site for SQL Server 2022 only. So let's get a little bit more into what the MI link feature is. As you can see with the green arrow, we're replicating databases from on-premise into SQL Azure. So we're maintaining an identical copy of your on-premise database within SQL Server in Azure. There's a link there you can use to learn more details. And this allows you to replicate data and offload analytics to SQL MI. You can use some of the interesting Azure Analytics functionalities on your SQL Server or on your MI database while keeping your core SQL Server running on-premise as it has using familiar tools and processes. You can offload read-only application workloads to SQL Server MI as well. So you send the read-write workload into SQL Server on-premise, and the read-only workload can read from the MI link SQL in Azure. And then when you're ready, you can just flip the switch and migrate everything into the Azure SQL Managed Instance. So it is a migration tool, and it is also a way to explore the Azure world. So how does this work? Link is based on distributed availability groups. So what we're doing is setting up a distributed availability group between SQL Server on-premise and an availability group set up within Azure. So connections between SQL Server and SQL MI are bridged using a distributed AG. Distributed AG spans different availability groups across domains and across platforms. Windows failover clusters not required, SQL Server 2017 and above. single node Windows failover cluster is required for SQL Server 2016. If you can use mixed versions of SQL servers to connect to SQL MI, as long as you're moving the data in that one direction. That works just fine. The other interesting capability here is that you can use your managed instance in this configuration as a DR site. As long as you're running SQL Server 2022 on-premise, they're compatible. So you can then fail over from your on-premise instance into your availability group in managed instance. And then when things are resolved back on-premise, you can actually fail back because we're managing the compatibility between those two versions. So that's a very new capability, and it's pretty exciting, opens up some pretty exciting possibilities there. Availability group perf and stability enhancements. So there's a few interesting pieces of work that have been done. They're kind of wonky behind the scenes, but they're very end up being very high impact. First is 2 TCP channels for log replication within distributed availability group environments. So distributed availability groups tend to have a lot of latency between the replicas because they're designed to go cross-site. By adding a second TCP channel, we get much better throughput across that availability group or distributed availability group link, and it unblocks what has been a choke point to this point. So you get much better throughput even in high latency environments. There's some redo thread pool enhancements. So if you think about a failover or any time the database is coming online, one of the operations that has to happen is redo. So we have to go through and redo any incomplete transactions in any database. If you have a bunch of databases, there can be problems with thread allocation. Previous to SQL Server 2022, we would statically assign threads at 100 threads per database. And if there were more threads after you had exhausted your number of threads, we would assign the remaining DBs get one logical thread each. If one of those remaining DBs happens to be a big important database that has a lot of work to redo, it's going to be a long time before everything is online. So what we've done is re-architected that whole scenario. Instead of having statically assigned threads to databases, even if the database isn't doing anything, which is what was happening, now we have a global thread pool for redo work. So there's a global set of threads that are dedicated to doing redo. And any database can post a work item on the queue for this thread pool and get a thread to do that piece of work, and then the thread returns. So it ends up being much more fair and efficient use of the execution threads. So rather than having threads sitting idle on a database that's already recovered, where another database that's trying to recover has no threads, now you have a much better utilization of your compute resources. Always on health, you can capture SP server diagnostics X events when state is 3 to diagnose HADR health events. There's a change to add reverting progress to error log, just like SQL already reports recover progress. So now you can find out more fine-grained detail of what is going on. If you're having to revert, you'll know that. Another DCR to improve always-on health and system health logs to add X events generally give you more richer information to do debugging and understanding what's going on within the system. And there's an unfair mutex being introduced into the UCS session registration to improve HE data movement. So this just means that we're, like with the thread pools, we're having a much more efficient way to allocate compute resources to work to be done in the UCS transport. Peer-to-peer replication with last writer wins, also known as write-write replication. So what this is about is if two replicas each update the same data element within a small time window, we have to figure out which one should be persisted, which one wins the conflict. Previously, the replica with the highest static ID would be the one that would win, regardless of which came first. So whether replica 1 or replica 2 did the update first, replica 2 update would always be the one that persisted. More often, you're going to want the replica that was updated most recently to be the one that persisted. That's kind of what logic would dictate. And that's what we've implemented here. So the conflict detection now comes to do with the last update is persisted across all replicas based on UTC time of the operation. So you don't have to worry about time zone issues. It's just when we do an update, we tag it with the UTC time that the update was made at, and then if there's a conflict, we will look at the timestamps, and whichever is the most recent is the one that persists. So what that looks like is at time t0, replica 2 updates row 1 to set a equals 45. Time t1, so that's after the first update, replica 2 or replica 1 updates the same row, same column to be 23. Final value. Without last writer wins, what happens is the replica with the highest ID, that being replica 2, wins, and thus the value is 45. With last writer wins, then we take the value of, based on the most recent update. So T1 having updated the value the most recently, that's the value that would persist. And if you think about it, if the time window was outside of the window that we look at, then obviously the last one to update that value would be the one that persisted. We're just bringing that same semantic into smaller and smaller time windows. So it just makes sense. And now we come to contained availability groups. This is one that I've been passionate about and very excited for a long time. So what are contained availability groups about? The problem statement, the problem we're trying to solve, is that when you set up availability groups, there are objects or settings related to the AG that are not part of the databases being replicated. So they don't get replicated across the instances. So users or logins, permissions, agent jobs, other settings, those have to be kept in sync manually. So those don't automatically get replicated. Even if you add a user or login within the context of an availability group, we're not going to replicate it to the other replicas in the AG. Applications need to have a consistent execution environment. They need to have the same logins available, the same permissions, jobs that run predictably regardless of which node happens to be primary. And so what happened is that users needing that consistency would invent workarounds, which are generally complex and fragile scripts, to force synchronization or to enforce manual processes. So someone would have to go and look and see if anything got out of sync and manually sync it, which was not the most fun process, and it's also somewhat error prone. So that's the problem, and I have heard these complaints since we first shipped availability groups in 2012. Now we finally have a resolution for those. So the goal is to provide a unified experience across all instances in the contained AG. So nearly all operations within the AG require no syntax change, the only exception being operations specifically impacting a contained AG. We preserve the operations and management of the individual instances in the contained AG. So we're not going to mess with your ability to manage one instance separately for the other where it doesn't conflict with the AG. And we're also enabling multiple contained AGs to coexist in the same set of instances without interference. So if you have AG1 and you've defined user 1 within that AG to be an AG-specific user, AG2
doesn't necessarily have that user unless you create it there as well, because it's contained within agent, within that AG. The syntax change is very simple. When you create the contained availability group, you now have a new bit of syntax which says contained, with contained. That's all that it takes to make the AG that you're creating a contained AG. Note that this is at AG creation time. You cannot convert a normal AG to a contained or vice versa. Once it's created, it is in one state or the other. We use system databases refers to, we have local system databases that are part of the AG. I'll get into that in more detail. And that just means that if we've dropped a contained AG and want to recreate it, we use that flag to tell it to reuse those system databases that were left by the previous version of this AG. The listener is an important characteristic, which I'll get into as well. Note, contained availability groups do not represent a security boundary. What we're doing is giving you convenience of keeping the settings and the logins and jobs and all that in sync. It's a synchronization mechanism. It's not a security mechanism. So just because you're within the context of a contained availability group, you still can see databases that are outside of it. So if you want to do a cross database with something that's on the local instance, you can do that. Just know that if you happen to be running on the other instance, your mileage may vary. To manage or interact with the contained AG, you connect to the contained AG either using the contained AG listener, so connect to the listener for that contained AG, or the connect string has to specify a database within the contained AG. So not use, but connect using myAG MSDB. And database names must be unique across all instances. So if you have mydb1 as part of contained AG, you can't have one of the member instances have a different mydb1. So how do we accomplish this magic? System databases are the secret to all of this, keeping all of this in sync across all members of the AG. We create AG-specific master and MSDB databases in each contained AG. So each contained AG will have a master, which is named the name of that AG. So accounting AG underscore master and accounting AG underscore MSDB will be part of the accounting AG availability group. Other contained AGs on the same instances will have other names because the AG name is different. These master and MSDB databases are initially empty, except that we will copy in the members of the sysadmin group will be added to these blank MSDB, or master database in this case, so that you can manage the AG as soon as it's created. And when you add new replicas to the contained AG, these databases are seeded along with the other databases that are part of that AG. And now, without further ado, I'm going to show you what contained availability groups looks like in action.
Hi, I'm going to do a quick demo of creating a contained availability group. I've got a script here that does all the steps. You know, it's running in SQL CMD mode, which means that I can connect back and forth between the two replicas, which makes the whole operation a lot simpler. So the first thing that we're going to do is create the endpoints. Now we'll grant connect on the endpoints. Note that we're going back and forth between the replicas. Next, we'll create the always-on health session, and then we go to the secondary replica and do the same operations. And then we'll create the availability group, and you note the only new syntax is contained. So we're going to go ahead and start from the beginning. Create the endpoints, create the availability group, You add the listener to then we connect to the secondary. And join the availability group. So that's running. So according to the results, everything went fine. So let's look. Here we see, we refresh the view, and we see all the objects. You see we have test CAG, which is the primary replica, and we have the different availability replicas and databases. Note there's a couple of new databases. I had wide world importers to start with. Now we have test AG, the name of the availability group, _ master, and MSDB. This is a mechanism we used for keeping the contents of the master database in sync across all the replicas. So now what I'm going to do is reconnect to testag _ LSN1, which is the listener for the contained availability group. We're connected to the contained availability group through the contained listener, which is what gets us into the environment of the contained AG. And then we're going to create some agent jobs, something that you normally would do and normally would have to go around to the other nodes and do the same job, create the same jobs, and make sure that they're executing in sync. We've done that now. So how do I show that everything has gone the way I say that it should? I'm going to connect first to replica 1, and then to replica 2, and then to the listener. At each point, I'm going to select add server name, the physical server that it's running on, and then do a select from sys jobs. So again, here test AG1, the instance doesn't show any agent jobs. Test AG2 also doesn't show any agent jobs. The AG happens to be running on test AG1, and you'll see that there's the agent job there. So all of this works good. So now I can go into test AG primary, and failover to see what things look like from the other side. Connect to the other side and start the failover. And I have success there. So now what I can do is to connect, change connections. So I can connect to the listener, test AG LSN1, which should be running on test AG2, and run the same query. And you'll see that indeed we are executing on test AG2 is there. I didn't copy it across, but now that we're running on the other replica, we have the same set of agent jobs, and that's the power of contained AGs.
Thank you, Kevin. Hello, everyone. My name is David Pless. We're going to wrap up with SQL Server 2022 backup compression and offloading with Intel Quick Assist technology, QAT. So in SQL Server 2008 Enterprise Edition, backup compression was introduced, adding with compression as an option in the T-SQL backup command. While customers leverage the current compression standard, the challenge many customers have with the current implementation is that the compression ratios are often too low to justify the additional compute overhead required to compress the backup files. Also, customers cannot offload the compute overhead of the compression task. So many customers in high volume OLTP environments put their business continuity and disaster recovery strategy at risk because they have to delay their regular backup schedules in order to remain operational for customer workloads. So there's a number of existing backup compression products already on the market for SQL Server. They're all software-based compression with their own drawbacks, and none of these are really integrated with the SQL Server engine. So customers have been looking for a way to get the compression they need, an integrated method to control the compression, and with the ability to maintain the support with their backup and restore strategy. So the solution is hardware offloading and acceleration. So Intel Quick Assist technology, QAT in SQL Server 2022, solves for these challenges by providing hardware acceleration and CPU offload capabilities for enhanced compression and decompression. This feature is designed to give improvements both in terms of reduced CPU usage, backup completion times, as well as a reduction in storage consumption. So the implementation of this feature extends the current backup command to make it straightforward for the database administrator to choose the desired algorithm to compress backups. The feature also surfaces appropriate error log and informational messaging so you can troubleshoot the Intel QAT configuration, as well as being able to track the benefits of the compression feature over time. With SQL Server 2022 in early testing using Intel Quick Assist technology, Intel witnessed over a 2x speed improvement and a reduction of 6% in the storage capacity consumed for the tested backups using internal workloads. Okay, so in order to back up databases with the Intel Quick Assist technology compression algorithm, it is required to have the drivers installed, and SQL Server 2022 must be permitted to load the drivers into the SQL Server 2022 process space. To complete this effort, there are 2 steps required to enable the hardware acceleration feature. You must first allow hardware offloading via spconfigure as shown here, and you must turn on hardware offloading choosing the accelerator and the accelerator mode where applicable. It is important to note that if this spconfigure hardware offload enabled setting is disabled, all accelerators for SQL Server 2022 will also be disabled. The default setting for spconfigure hardware offload enabled is to have the capability turned off. As shown here, an option has been added to alter server configuration in SQL Server 2022 with the hardware offload syntax to enable or disable the use of hardware acceleration for a SQL Server instance. With this configuration being applied after a restart of the SQL Server service, the Intel QAT hardware acceleration technology can be used to provide a new optional backup compression algorithm. After the feature is enabled, every time SQL Server starts, the SQL Server process will look for the required user space software library that interfaces with the hardware acceleration device driver API and will load the software assemblies if they are available. The unavailability of an Intel QAT device will not prevent SQL instances from performing backup or restore operations using the new QAT deflate algorithm. If the physical device is not available, the software algorithm will be leveraged as a fallback solution. You can disable the hardware offloading by performing the same alter server configuration setting and turning the hardware offload to off. A server restart is required for this setting to be disabled. Customers may choose to leverage software-only mode versus hardware with software fallback. This may be preferred if you have a higher amount of computing resources and would prefer to optimize for backup performance over protecting the host system's compute resources. The example shown enables SQL Server to load the Intel QAT binaries for software-only use. With either alter server configuration example, after executing the statement, users must restart the SQL Server service to load the Intel Quick Assist Technology QAT binaries into the SQL Server process space. The T-SQL backup command with compression has been extended to allow for a specified backup compression algorithm. When using Intel QAT for backup compression acceleration, the algorithm QAT deflate will initiate an Intel QAT compressed backup if the drivers are available and the SQL Server configuration has been completed successfully, as illustrated in the previously documented steps. The algorithm command will be used to specify either of these two algorithms, MS Express or QAT deflate, for backup compression. The example shown here will perform backup compression using Intel QAT hardware acceleration. We would surface an error if the statement was run and the Intel QAT drivers are not available. Now, to use the traditional backup method, all you would need to do is run the backup database command just as we did before and specify either with compression having the algorithm equal MS Express or by simply running backup database with compression without the algorithm specified, as MS Express is the default. Here we see an example of this that would have been valid syntax on any release of SQL Server. Backup database to disk with compression. This command will use the default compression algorithm, MS Express. Running restore header only on a backup without compression and a backup compressed with the default MS Express algorithm will return results similar to the ones shown in the slide. The restore header only command will display the compression algorithm along with other information such as backup name, backup description, backup type, compression state, device type, and other columns. In SQL Server 2022, restore header only adds the compression algorithm column. Restore header only displays the compression algorithm. If it's an Intel QAT backup, we need Intel QAT drivers to be loaded. Otherwise, there'll be an error which tells users to enable Intel QAT in order to read the compressed Intel QAT backup. The restore command does not include a compression option, as the backup header metadata specifies if the database is compressed, and therefore the storage engine can restore from the backup files accordingly. The backup metadata will be extended to include the compression type. Backups that have been compressed with either QAT deflate or MS Express and uncompressed backups will all use the same T-SQL syntax restore database DDL commands. In the example shown, the T-SQL restore syntax is valid for restoring from the database file, regardless of whether it is uncompressed backup or a compressed backup using the QAT deflate or MS Express algorithms. SQL Server database compressed using QAT deflate will support all T-SQL restore operations. The restore database or log statements for restoring and recovering databases from backups will support all recovery arguments, such as with move, partial, stop at, keep replication, keep CDC, and restricted user. If the server scope configuration hardware offload option is not enabled and or the Intel QAT drivers have not been installed, an error will surface instead of attempting to perform the restore. You'll see an error similar to this operation requires Intel Quick Assist technology libraries to be loaded, along with the completion time for the operation. To restore an Intel QAT compressed backup, the correct assemblies must be loaded on the SQL Server instance, initiating the restore operation. In order to verify the SQL Server 2022 accelerator configuration, a number of methods can be leveraged, including a new dynamic management view, the sys configurations catalog view, and the SQL Server 2022 error log. The methods shown here can assist in validating and troubleshooting the SQL Server 2022 accelerator configuration. The SQL Server sys.dm server accelerator status dynamic management view can be used to verify the Intel Quick Assist technology configuration state. This dynamic management view should be used to verify the SQL Server accelerators that are available on the SQL Server instance and the configuration status of the accelerators, displaying the mode description reason, hardware availability, the configured libraries, and the driver versions confirmed to be loaded. It is recommended to leverage the Intel Quick Assist technology landing page to get the latest drivers, hardware product support, and guidance from Intel. Leverage the SQL Server error log for troubleshooting. For the Intel Quick Assist technology compression feature, we can identify the system manufacturer in the error log along with the compression library, kernel driver, and the storage acceleration library. It is recommended to verify that the initialization was successfully completed. You can verify whether or not the hardware was identified on the system and if software fallback was leveraged. In the example on the slide, we can see that the SQL Server 2022 Enterprise Edition instance is being leveraged with an Intel Quick Assist technology device discovered and operating. Notice the library version for Intel QAT-zip, the kernel driver version, and the Intel Storage Acceleration Library, ISIL, and the Intel Quick Assist Technology Success Messaging. Okay, so we're going to do a quick demo taking a look at the Intel QAT backup compression feature. Okay, so the first thing I'm going to do is show advanced options and ensure that hardware offloading is enabled. This will allow me to load any accelerators into the SQL Server process space on startup. I'm going to go ahead and run this now. Okay. And we are going to do an alter server configuration and set the hardware offloading to on and enabling the accelerator for QAT. And the mode we are going to use is software in this case. So I'm going to go ahead and run this. And I will now need to restart the SQL Server service. And I will do that now. Okay, so now that this has been done, let's confirm the state using the sys.dm server accelerator status dynamic management view. And we can see here that the QAT accelerator, this is the Intel Quick Assist technology. Okay, we are using software mode, and we can see that we forced it. That's what the mode description is showing us here. I can see the library as well as the driver version. Okay, now I can also check the error log for this information as well. And we can see that here. And I'm going to expand this and zoom in so we can take a quick look. We can see that the Quick Assist compression library is being shown, the kernel driver. We can see that the Intel Quick Assist technology was initialized correctly. And we can see that it saw the hardware, but we also know that we are using software mode via the configuration from the dynamic management view. Okay. What I'm going to do is first run with the default MS Express compression. I'm going to go ahead and run this, and I'm going to capture this information. Okay. So I'm going to take this data, paste it in right here for comparative analysis. And now I'm going to run the same kind of backup on the same database using the QAT deflate algorithm. Okay. And we certainly can see that the QAT deflate algorithm was much faster in terms of time as well as throughput. So we're seeing 7.5 seconds for the MS Express default, 1,459 megabytes per second throughput versus 5.695 seconds for the QAT deflate algorithm at 1,923 megabytes per second throughput. Okay, so that's just comparing MS Express to QAT deflate, seeing this capability in action. And what I'm going to do is also show you the restore header only that we talked about in the slides previously. We can see that by comparing these two, I can see the compression algorithm here. So MS Express shown here versus QAT deflate in the compression algorithm. So I certainly know the drivers are available for the system, and I can see that using the restore header only comparing these backups. And lastly, I'm going to run this query here. Now I didn't mention this in the slides, but we have added the compression algorithm to the msdb.backup set catalog view in the MSDB database that allows us to see the compression algorithm over time, run a number of backups on the system so I can kind of track the health of my backup experience, showing which compression algorithm I'm using. So QAT deflate versus MS Express versus not compressing at all, being able to kind of get a history of that experience. And that is the feature that we have here of using this capability to get much better performance around your backup and restore strategy using the Intel Quick Assist technology, QAT experience in SQL Server 2022. Thank you so much for watching, and thank you to the data platform geeks and SQL Server geeks. Really quick, you can win some prizes by posting your selfie with a hashtag DPS2022. Please give session feedback and visit sponsors, and don't forget to follow the Data Geeks and Data AI Summit on Twitter, and follow me, Pless, as well as Kevin Farlee, for the latest on SQL Server 2022 and storage engine topics. Much thanks, everyone.